Okay, I'm going to talk about double replacement reactions. So a double replacement reaction can also be called a double displacement reaction. And basically what it is you have two compounds that exchange ions or potentially exchange elements to form new compounds. So the most common type that you deal with involve ionic compounds. That's why I say it exchanges ions. But you could have molecular compounds where, the elements essentially split up and swap partners. Now, most of the time when you deal with double displacement reactions, people will kind of classify them a little more specifically because there's several different types of reactions that kind of fall in this category. And so there's three that we're going to talk about and go into a little more in depth. The first one's precipitation reactions. So this is probably the most common type of double replacement reaction that you would run across as a precipitation reaction. That's a reaction where a solid is formed when you combine aqueous solutions. So you start with two liquids essentially, and so two solutions of things, and you put them together and you get a solid. Another type of double replacement reaction is a gas formation reaction. And so this, as the name suggests, forms a gas. But this type of reaction can form the gas directly from the double replacement, or after the double replacement reaction occurs, then something can break down further, forming the gas. And then the last one that we'll talk about is acid-base neutralization reactions, which I clearly have a typo here. This should say acid-base neutralization reactions. And so that also is what it sounds like. You have an acid and base and they neutralize one another. And so we're going to look at each of these types of reactions a little more in depth and look at some examples of them. So first, let's look at precipitation reactions. And so a precipitation reaction, again, is when a solid forms when you have two solutions that are mixed. So for this, the solutions mixed, those actually typically contain soluble ionic compounds, okay? You could have, say, an acid or base involved, but you wouldn't usually have an acid and base, although you could, but then be multiple types of reactions at once. So for the most part, when you think about a precipitation reaction, you should think usually you have two solutions of ionic compounds, you mix them together, and what happens is a solid forms. And that solid we call the precipitate, okay? And that's going to be some insoluble ionic compound that forms. So essentially you have these solutions of ionic compounds that you mix, and those are soluble, meaning really you have solutions where you have a bunch of free ions floating around. Because when you have a soluble ionic compound and you put it into water, those ions break free and they're all surrounded by water. So then when you combine those two solutions, what happens is some of the ion partners swap and form then an insoluble ionic compound. So they form the precipitate. Now, if you're just given, say, two solutions, or you're given the reactants and asked to predict what the product would be, what you need to do is you need to be able to identify what ions are present to start with, and then you're going to swap the ion partners. So initially you have some cation and anion that came from one compound, and then a cation and anion that came from another compound, and so you'll swap partners. So the ones that came from the same solution will essentially split up and partner up with the ones from the other solution. And then once you predict those products, you would determine the phases of the compounds, meaning you would determine, is it dissolved? Is it aqueous? Meaning, is it a soluble ionic compound? Or is it insoluble, meaning the phase is then going to be a solid? So let's look at one example to start with on kind of what I'm talking about when I say swap ion partners. So this example says to write the balanced chemical equation for the precipitation reaction between aqueous solutions of magnesium nitrate and potassium phosphate. So I give you the reactants. It's two aqueous solutions, and then I want to know, or I want the balanced chemical equation. So you're going to have to be able to predict products and then determine phases and balance the reaction. So we'll start off with these compounds given. So magnesium nitrate, that's an ionic compound, right? It's a metal with some nonmetals. So you need to know the formula. So it would be helpful to first think about the ions. You have Mg2 plus is magnesium ion, NO3 minus is nitrate ion. So when those come together, magnesium nitrate is actually Mg NO3 2. Okay, you need 2 nitrates for every 1 magnesium to make a neutral substance, and that's aqueous. And then we have potassium phosphate, and so that's another ionic compound made up of potassium ion and phosphate ion. And so that comes together with K3PO4, because you need 3 of the K pluses for every 1 PO4 3 minus to make a neutral compound. And so then that's also aqueous because our starting solutions are aqueous. Now to predict the products, what we're going to do is we're going to swap ion partners. So I wrote out those ions when I was figuring out the compounds. If I was directly given the formulas of those compounds, I would first write out the ions. And then we're going to swap partners. So we're going to look at the cation of the one, and that is going to want to combine with the anion of the other compound. So the magnesium ion will combine with the phosphate. And then the cation that remains will combine with the remaining anion. And that's going to give me my products. And so then if magnesium ion combines with phosphate, I'm going to need to combine them in a 3:2 ratio to make it neutral. So I'm going to have Mg3PO42. Oops, not a charge. 2 is a subscript. Go. And then K plus with NO3 minus would be KNO3. And make sure you're always writing your cation before the anion. Okay, so those combine 1 to 1 because a +1 and a -1 makes 0. Now the phases. I need to put the phases on here. And as I say above, you determine that using solubility rules. Okay, and so solubility rules just tell you based on particular ions that are contained what is likely to be soluble and insoluble. Now, a lot of times, you find a list of solubility rules, and there's going to be some things that are generalized. It's not going to be perfect. So you got to pay attention if they say there's exceptions, or you have to be aware that they may not list every possible exception. But you use a set of rules to figure this out. So I've actually got a table of solubility rules, and in this, it tells you about ions. So you have to focus on the ions contained in the compounds. So if we go back, we have magnesium phosphate. So if we go to that table and you look in there on the left and look for the ions, there's no magnesium shown, but there is phosphate. So they say phosphate, and they say most carbonates, phosphates, sulfites, and silicates are insoluble. Okay, and then they give you some exceptions. Exceptions include Na plus, K plus, and NH4 plus. It would really be any group 1 metals along with ammonia. Okay, and so that tells me that that phosphate must be insoluble, meaning that it is a solid. It does not dissolve, so it precipitates out when it forms. And then I can look for KNO3, so I would look for K plus, okay, and K plus, it tells me most compounds of alkali metals and ammonium ions are soluble. and it doesn't give you any exceptions. And so based on it having K plus, or really if it had any other alkali metal, we would say it's soluble, meaning we would write it as aqueous because it remains dissolved. Now on this one, you could also look at the nitrate. So it was KNO3. You could look at this nitrate and it tells you nitrates are soluble. Okay, all nitrates. And so that would also tell you it's soluble. So you could really look at the cation or the anion. You just have to pay attention. Does it give you any exceptions? And once one of those things tells you that it's soluble or insoluble, that gives you the phase. So in this case, it's soluble, so we write it as aqueous. And so that's my reaction, but I need to balance it still. So for this, let's see, we have got 3 magnesiums on the right, so I'll put a 3 in front of there. And now that gives me 6 nitrates. So I'm going to put a 6 in front of the KNO3. And then I'd need 6 potassiums, so I'll put a 2 in front of the K3PO4. And that gives me 2 phosphates, and I have 2 phosphates on the right. So that's my balanced chemical equation. And so you're just swapping ion partners. So let's look at a few more where you're actually just given reactants. So again, here's the solubility rules. This is something that some of these things people assume you kind of know off the top of your head, like group 1 metals and ammonium ion. If that's in a compound, it's soluble. Or if nitrate's in a compound, it's soluble. When you see things like carbonate and phosphate, most often it's insoluble. So after you refer to these rules enough times, some of the stuff should start sticking, but otherwise just know that if you need to determine is this soluble or not, so you can determine if you label it as aqueous or not, you would look at the solubility rules. And this is for ionic compounds, okay? So you don't use this for molecular compounds. This tells you about the solubility of ionic compounds. So let's do a few more predicting products of reactions, okay? So here I say predict the products of each of the following reactions and provide the balanced chemical equation. So here I've got ammonium sulfate and strontium chloride. So the first thing you want to do is split it up into ions. So ammonium sulfate is made up of NH4 plus and SO4 2 minus. Fix that 4 here. So that's my cation and anion. Now notice I dropped that 2 subscript. The only reason that 2 is there is just because you need 2 of the ammonium ions for 1 sulfate. But that's not part of the ion. So that part gets dropped. And then the other compound, the strontium chloride, that's made up of strontium ion, which is Sr2 plus, and chloride ion, Cl minus. Okay, and again, I dropped that subscript 2 from the chlorine because the only reason it's there is because I need 2 of the chlorides for every 1 strontium. Okay, so that's not part of the actual ion. That's just part of the ratio to make it neutral, which when you pair it with something else, that subscript may need to change. So that's why we dropped it. Now you're going to swap partners. And so we would take the cation of one and combine it with the anion of the other. And then the remaining cation and anion come together. And so then my products would be, well, I have NH4 and Cl minus, or NH4 plus and Cl minus, so I need 1 to 1. So it's NH4Cl. And then we've got Sr2 plus and SO4 2 minus. And so that's a 2 plus and a 2 minus. So 1 to 1 ratio for those. So Sr, SO4. And then I need to figure out the phases. So I'd look at the solubility. So we have NH4Cl and NH4, that's something that's soluble. There's no exceptions given. Okay, so that means that that one I would list as aqueous. So anything with ammonium ion is going to be aqueous. And then we have strontium sulfate, And what you can find in the list is sulfate, and it tells you most are soluble, but it gives you exceptions here, so you have to pay attention. Here it says an exception is strontium sulfate, so that's insoluble. So that one is actually our precipitate, so we would write it as a solid. Okay, and that's our products, but then we need to balance it, and to balance it, we need a 2 in front of the NH4CO. Okay, the next one, we've got Li2CO3, so our cation is lithium ion, so Li plus, and our anion is CO3 2 minus. Okay. And then for the other one, we have cobalt. Now, cobalt can have more than one charge, so I don't know the charge of that yet. I have to base it on the anion that's there. So the anion C2H3O2, and if you don't know the charge of that, you look it up in a table, and that's always a -1. And if there's 3 of those with one cobalt, then the cobalt must be a 3+. Okay? And again, just like before, I dropped some of the subscripts. I dropped the 2 on lithium because lithium isn't a polyatomic ion ever. And then I dropped the 3 off of that polyatomic because I just needed 3 of them. Okay, that isn't one of the subscripts that's part of the ion. Okay, now we need to swap ion partners. So the lithium ion goes with the acetate ion, and then the cobalt 3 goes with the carbonate. And then my products, I just put them in a ratio to make it neutral. So Li plus and C2H3O2 minus, I need 1 of each. So it's LiC2H3O2. And my other product is I need a 2-to-3 ratio, so 2 of the cobalts with 3 of the carbonates. Again, you have to put it in the order of cations listed first always. Okay, so those are my products. I need the phases. So if you went back to the table, then what you see here is you have Na plus and K plus and NH4 plus, and then it says and other alkali metal ions. Well, that would include lithium, okay, is one of them, and that's soluble. So that one is aqueous. You could also have looked up acetate ion and it would tell you it's soluble. Then the next one we have cobalt-3 carbonate. So if we look at carbonate, because cobalt's not on that list, tells you most carbonates are insoluble and exceptions are the group 1s and ammonia. So that's not an exception, so it's insoluble. So this one is listed as a solid. And then we need to balance the reaction. We need, let's see, 3 carbonates. We need 3 of the acetates. And then that makes 6 lithiums. Well, I'm going to go back. I jumped around kind of crazy here. So I did 3 carbonates because we have 3 carbonates in the end. And then I'd need 6 lithiums. And then the cobalt, I need 2 of those, so I need a 2 in front of here, and that would make 6 acetates. So then it's balanced. Okay. So I've got that done. It's balanced. Got my phases. Okay, and I've got my products. So then the next one, I've got lithium sulfide. So the ions, I've got Li plus and S2 minus. And then iron 3 nitrate, so it's Fe. And if you didn't know it was iron 3, well, the NO3 part has a constant charge. And if you don't know it, you look it up and it's a -1. So if there's 3 -1s, this must be a 3+. Okay, oops. And so then we swap ion partners. And so the Li plus goes with the NO3 minus and the Fe3 plus goes with the S2 minus. And so then my products are going to be LiNO3 And that's going to be aqueous because it's got a group 1 metal. Those are always soluble. Same with nitrate. And then I would have Fe2S3. And if you look at the solubility table, what you'll see is sulfides are insoluble. Exceptions are your group 1s, ammonium, and group 2 metals, which iron is not. So that's insoluble, so that would be a solid. Okay, and then to balance it, what do we need? We need 2 lithiums. Well, we need 3 sulfurs, so we actually need 6 lithiums, and then 2 irons, and that gives us 6 nitrates and 6 nitrates. So then that would be balanced. Okay, now we're going to do a few more examples here. We just won't do the full reactions. So this next question says, what will the precipitate be if you mix aqueous solutions of the following ionic compounds? Okay, so this just wants to know the precipitate. So we don't need the full reaction. We just need to find the precipitate. And so we need to look at the ions. So silver nitrate is made up of silver ion, so Ag+, and nitrate ion, NO3-. And then magnesium chloride is Mg2+ and Cl-. Okay, and those are aqueous solutions of those things, meaning the Ag+ and NO3- aren't going to make a precipitate because it's already aqueous solution. And Mg2+ and Cl- will not make a precipitate. It's already an aqueous solution. So what you need to look at is, will Ag+ and Cl- form a precipitate, or will Mg2+ and NO3- precipitate? Okay. Now, this one contains nitrate, which is always soluble. And so that means that this one is not a precipitate. Okay. So then the question is when Ag and Cl combines, is that a precipitate? And if you go back and look at the solubility table, what you'll see, focus on just what's going on right now. We look, we've got Cl, and it says most chlorides, bromides, iodides are soluble, but exceptions are AgX, where X can be ClBr. So that one is insoluble if you have AgCl. Okay, so that means that when we combine Ag+ and Cl-, you're going to get the precipitate AgCl. And so that's the answer for that first one. And then this next one, we look at the ions. This gives you K+ and CO3 2-. And then the second one is made up of Pb2+ and NO3-. And so if we look at what could combine, so the K+ and NO3-, the Pb2+ and the CO3 2-. Well, if you have K+, that's a group 1. Okay, this is a group 1, meaning that's always soluble. Doesn't matter what it combines with. Okay, based on the solubility rules. So that one's soluble. So that's not our precipitate. But then this other one, you've got carbonate. And carbonates are usually insoluble. There are a few exceptions. That's the group 1s and ammonia. And so this one is insoluble. So this would form PbCO3. That would be the precipitate. Okay. So for this question, it just specifically asks what's the precipitate. And so you don't really need to write the whole reaction, but it could be helpful. So I kind of shortcutted. I didn't write the entire reaction, but you could if that's helpful to you. And we'll do one more set of examples. Here it says, which of the following will result in a precipitation reaction? And so the only way you're going to know if you have a precipitation reaction is if you figure out, will some insoluble compound form? So you've got to predict the products. Okay, so even though it doesn't say predict the products or what is the precipitate, it just says will a precipitation occur. The way you figure that out is you identify if there's a precipitate. And so again, you look at the ions. You have Pb2 plus, you have NO3 minus, you have K plus, and SO4 2 minus. So you've got to be able to break down ionic compounds into their ions properly. And then you've got to pair them back together. And so if we pair these together and these together, what do we get? Well, K plus and NO3 minus can come together and form KNO3, but nitrates and potassium salts are always soluble. So that one is just going to be KNO3 aqueous, because based on the solubility rules, those things are always soluble. But then our other one's going to be PbSO4. And if you look at the solubility rules, what you'll see is sulfates are usually soluble, but when it's with lead 2, that's an exception. So that one is actually a solid. Okay, so since there's a solid formed, then yes, there is a precipitation. Okay. So there is a precipitation reaction that occurs. if I could spell here, precipitation. There we go. That's better. Okay, next one. Now I've got Na plus, SO4 2 minus, and then NH4 plus, and NO3 minus. So if you combine these, you get NaNO3, and you combine Na plus and NO3 minus, and that's got a group 1, so it's soluble. Also, it's got nitrate, so it's soluble, so that's aqueous. And then, what else do we have? We have ammonium combined with sulfate, so that would be NH4 2SO4. And that has the ammonium ion. And anything with the ammonium ion is soluble, so that's aqueous. Okay, so this is no precipitation because no solid forms. And so you could say that there's no precipitation reaction. Usually we would just say no reaction. Okay, so even though you can predict those products, swapped ion partners, it doesn't mean it actually happens. Okay, so a solid would actually need to form. Now this last one, we've got NH4 plus, CO3 2 minus, and then we have Zn2 plus, and NO3 minus. Okay, so I know I'm starting to go through these faster, but you got to get the hang of it. You've got to be able to break the ions down, or break down the compounds into ions, and swap partners, so the NH4 plus with the NO3 minus. Now, if you look those up on the solubility rules, you'll see both of them tell you that they're always soluble. Okay, so this would be aqueous. Okay, and then our next one would be the zinc and the carbonate, so ZnCO3. And what you'll find is information about carbonates that tells you that they're insoluble most of the time. Zinc is not an exception, so it is insoluble. So that's our precipitate. So yes, this is a precipitation reaction. Okay. Okay. Hopefully that's enough practice. I did several precipitation reactions. I did so many of that one because that's the most common one you have to deal with. You have to be really good with predicting products of precipitation reactions, understanding when we would say mixing these substances results in no reaction. So if no solid forms, you've got to be able to use solubility rules. Whether you have them memorized or you're looking them up, it doesn't matter. But you have to be able to apply them to figure out the phases of things. Now, let's talk about gas formation reactions. So as I said, this is what it sounds like. A gas is formed, okay? But it could form directly or it could form kind of as a secondary product. So first, if we had, say, the reaction of some sulfide with an acid, that's going to form H2S because the sulfide compound, the anion is S2 minus, and that's going to combine with the cation of the acid, which is H plus, meaning no matter what sulfide you have, if it's reacted with an acid, it forms H2S. And H2S is a gas, okay? Yes, when H2S is dissolved in water, it is an acid, but that is something that is going to naturally escape the solution in the gas phase. Okay, so although temporarily it could initially be dissolved, it isn't going to stay in solution long. It's just going to bubble out there, meaning it is a gas evolution reaction. So I have an example here of sodium sulfide reacting with hydrochloric acid. But you could change out sodium sulfide for any other sulfide compound. So anything with sulfide. And then the acid, the HCl, could be swapped out for any other acid. And you would have a double replacement reaction. So it swaps ion partners. The Na plus combines with the Cl minus, and then the H plus combines with the S2 minus. But that H2S that's formed will go into the gas phase. So that's why it's called gas evolution. Now, the other type is you could have it form kind of indirectly. So initially, you have some sort of acid that forms, and then that acid breaks down and forms a gas. Okay, this is really common when you have carbonates. So if you have something like calcium carbonate, for instance, if you react it with an acid, what it will initially form is carbonic acid. And then that carbonic acid will decompose. So it'll break down and form water and CO2. And so that CO2 is a gas. Okay. So really what I have written first is the basic double replacement reaction. So we have the calcium is the metal and it's combining with the non-metal, the anion part of that, okay? Whereas the carbonate is combining with the cation part of the acid, the H plus, and so they swap ion partners and form calcium chloride and carbonic acid, but that carbonic acid, that's not really a stable molecule in solution. It will break apart, okay? It'll decompose, and when that decomposes, you get the CO2 and H2O, okay? So the second one I have written there is really the complete reaction that occurs. The first one is kind of the initial step, but it breaks down further. So those are examples of gas formation reactions. Another pretty common compound that forms gas reactions or does gas formation reactions is when you have sulfites. So when you have compounds with SO3, 2 minus as the anion, when those react with acids, they do the similar thing to the carbonic acid. They first form sulfurous acid, which then forms SO2 gas. Those are going to be the most common type that you would potentially run across. In this class, really the ones that we deal with is the ones involving carbonates, because those are pretty common compounds that we deal with. We don't deal with a lot of sulfides and sulfites even. But if you go into, say, an environmental field, gas evolution reactions or gas formation reactions are really common. And so if you did go into like an environmental field, you may do more with gas formation reactions. Okay, now acid-base neutralization reactions are also like they sound. It's neutralization of an acid and a base, but let's talk about kind of the pieces of the reaction. So in an acid-base reaction or acid-base neutralization, of course you have an acid. And you have to remember an acid is something that releases hydrogen ions or H plus. Okay, so maybe I should write that down for you. H plus is what I'm talking about when I say hydrogen ion. And then the base releases hydroxide ions. Now that's either directly or indirectly. So there can be complicated bases. We're going to keep it simple. So when I say it releases hydroxide ion, that means that in that compound initially it contained OH minus bound to some metal ion, and it splits apart and releases that. Okay. And then what forms as a result is a salt and then water. Okay, so the salt is actually formed by the missing pieces of the acid and base. So I say an acid releases hydrogen ions, but it's got to have hydrogen ion and it has an anion. Okay, so it's not only made up of hydrogen ion. There's some anion, and that anion's different depending on what acid you're talking about. And then the base, it's not only made up of hydroxide ion, it's some cation with the hydroxide ion. So what happens is that that anion and cation, those come together and they form the salt. Okay, whereas the H plus and the OH minus, those two things come together and they form water. Okay, and so that's always what's going to happen in an acid-base neutralization reaction, or at least in the simple ones. You can have ones that are a little more complicated than that, but when we talk about acid-base reactions, at least for now, that's what we're talking about happening. You always have some acid reacting with some base, forming a salt and water. And when I use that term salt, remember that is kind of a generic term for an ionic compound. Okay, and the ionic compound that forms depends on what acid and what base was being reacted. So let's look at an example here. This says to write the balanced chemical equation for the precipitation reaction between hydrobromic acid, which hydro and ic acid, that comes from the monatomic anion. Okay, so Br minus, and that must be combined with H plus to get the acid. So the acid is actually HBr. And since it's an acid, it's aqueous. And then potassium hydroxide. Okay, and so that is K plus for potassium and OH minus for hydroxide ion. And so that would be KOH. Now this actually doesn't say if it's an aqueous solution or not. Kind of doesn't matter in here. You could take solid potassium hydroxide and put it into a solution of hydrobromic acid, and it'll dissolve. Or you could put it in water first. So I'll just go ahead, I'm just going to label it as aqueous and assume that it was already in solution. And so then to figure out the products of that, you go through the same processes you do for precipitation reactions or any other double displacement or double replacement reactions. You take the cation of one, combine it with the anion of the other, right? And then the remaining cation and anion come together, okay? And so that means I get H2O, which is a liquid, and then I get KBr. And that's soluble, so it's aqueous, okay? And so that's my water, and my salt is the KBr. And that one actually is already balanced as is, okay? Okay, now let's do a few more predicting products of acid-base neutralization reactions. And so here I give a few sets of acid-base reactants. And so in the first one we have sulfuric acid, reacting with aluminum hydroxide. And so focus on the ions. Sulfuric acid is made up of H plus and SO4 2 minus. And then aluminum hydroxide is made up of Al3 plus and OH minus. Okay, and so you swap ion partners. And so the H plus goes with the OH minus and the Al3 plus goes with the SO4 2 minus. And so the products are H2O and, well, Al3 plus and SO4 2 minus, I need a 2 to 3 ratio, so Al2 SO4 3 to make it neutral. And then you need to figure out the phase based on solubility rules, because this is an ionic compound. So you look at the solubility rules, it'll tell you sulfates are usually soluble, and aluminum is not one of the exceptions, so we would label it as aqueous. And then you can balance the reaction. You would need 2 aluminum hydroxides because there's 2 aluminums. You need 3 of the sulfuric acids because there's 3 of the sulfates. And then if you focus on either the H plus or the OH minus, it'll tell you how many waters. So in 3 sulfuric acids, there's a total of 6 H pluses. So there's 2 per acid molecule, and there's 3 of those acid molecules. So you're going to have 6 H pluses, so you're going to get 6 waters. Okay, the same would go if you looked at the aluminum hydroxide. Each aluminum hydroxide gives you 3 hydroxides, and you're using 2 of those total molecules, so 6 in total OH minuses, so you would get 6 waters. Okay. Alternatively, you can count the hydrogens and oxygens individually. Feel free, I'm not going to do that. Now the next one, we've got phosphoric acid, so that's made up of H plus and PO4 3 minus, and then sodium hydroxide, so Na plus and OH minus. And so then, as always, swap ion partners, H plus and OH minus go together, and then Na plus and PO4 3 minus go together. So that would give us H2O liquid and Na3PO4. And so that, it's got a group 1 metal, so it's soluble. So that's aqueous. And then I'd need 3 of the NaOHs. And that means I'm going to make 3 waters. Okay. I know some of this stuff I'm doing fast. If you need to slow down, you can pause it and try to do it and then watch for the answer. Okay. Now let's see, last one, carbonic acid, we have H plus, and then CO3 2 minus, and then we have Mg2 plus, and OH minus. And so we will combine H plus and OH minus, and the Mg2 plus and the CO3 2 minus. Okay, so it would give us H2O liquid and MgCO3. If you look up, carbonate is typically insoluble, and so we're gonna call that a solid because the magnesium should not be an exception to that. And then let's see, if we look at the balancing, it's going to end up, you need 2 waters. Okay, so those are just, you know, a few examples. You should be able to predict products of acid-base reactions. It's just like when you're trying to do precipitation or gas evolution, you always split things into ions and then swap ion partners, at least to get started, then balance things.